Right. So thanks. First of all, thanks a lot for the invitation. I'm not an hardcore dynamicist, so it's a little bit of outside of my comfort zone. Even though I work on dynamics every now and then, I will ask specifically next conference I go not to talk after Marta Volonteri because she always put pressure like Alberto will explain you, Alberto will tell you that, and I'm not sure I have any answer really. But today I will talk a little bit about the last scale. So Marta gave the let's say the big picture, and then from Fanny we heard about the dynamical friction phase, and I will talk a little bit about the last parsec, okay, between when the binary formed a Keplerian bound system up to merger. And I will talk a little bit about the classical picture, like binary dynamics in stellar environment. And then the second part of the talk would be about triplets. So just to put things in context, why we care about this is because we know that galaxies are the galaxy formation is hierarchical. And if you start off with some seed black hole in protogalaxies high redshift, following galaxy mergers, this black hole will hopefully sink to the center and form binaries and eventually grow in mass and form the supermassive black hole we see today. So this is a very detailed simulation from Marta 2003, right? But of course we don't know, binaries will inevitably form, but we don't know much about their properties, their dynamics, their interaction and feedback with the host galaxies and so on and so forth. Of course, all of this is particularly interesting. I had a fantastic slide about Lisa, but I missed it. It's particularly interesting because this binary is going to be the loudest gravitational wave sources at millihertz and nanohertz frequencies. So just suppose there is a slide here showing the Lisa sensitivity curve, where the laser interferometer space antenna will operate in hopefully 10-15 years from now, 10-15 years from now. And in the nanohertz frequency where pulsar timing array are already collecting data and hopefully will detect something. So in this talk I will talk a little bit about the dynamics of this system and in particular the triplets and some interesting consequences for pulsar timing and Lisa. So Marta already showed a plot similar to this after galaxy merger. So I see Fanny and I have the same Google sources for our merging picture of galaxies. Right. So the dynamical friction phase, the binary pairs, but then at some point, when the two black holes start to see each other, their velocity becomes much faster than the typical velocity of the stellar background, and sort of they decouple from the background, and dynamical friction is not efficient anymore. So you have to rely on other mechanisms. And I will focus in this talk about stellar interaction with stars, okay? So the problem in hand is the fact that binaries will shrink because of dynamical friction to, let's say, parsec to a few parsec scale depending on their mass. But the timescale for dynamical friction becomes formally infinite. And you want them to coalesce because of gravitational waves. But the gravitational wave coalescence timescale goes with the inverse power of the separation, okay? And here, somewhere here, you have the Hubble time. So if you cannot bridge that gap between parsec and centiparsec, let's say, you don't have sub-parsec binaries that emit gravitational wave for Lisa and pulsar timing, which is bad. So let's see a little bit about stellar environments. So we'll talk about stellar, gas-poor environments only, okay? So you already saw this plot here. It's exactly the same figure, just 90-degree rotation, and I added the second black hole here. So now this is a loss cone for a binary supermassive black hole. So all this fuss about the last parsec problem started when early simulations showed that after you form a binary, the binary interacts with the star, it ejects stars because of three-body scattering, but then you run out of stars. So your binary is, in a sense, starved. And you see this depiction here in the angular momentum energy plane. Essentially, this is the portion of this phase space where stars would interact with the binary, but if you deplete that because you eject the stars and the star cannot diffuse very quickly, right, then your binary stalls, cannot interact with the stars anymore. So it was sort of soonish realized that this was largely, at least in the numerical setup, a problem of the simulation, of the oversimplification of the simulation themselves, in a sense that the first simulations assume a spherical distribution and just drop a binary in there, right? So, and I think there is like sort of a, I would say, general consensus that when you consider more realistic situation like a merger, a galaxy merger, the properties of the star distributions are such that this, stalling issue is much less severe. And the first simulation actually successfully merging a binary was from Peter in the audience, 2006. So what happens when you actually merge two galaxies? Well, in general, the merger remnant is going to be not spherically symmetric, possibly triaxial, possibly generally triaxial, possibly rotating. So this is a plot of triaxiality as a function of time for let's say spheres including different amount of mass, fraction of mass of the galaxy. So you see, especially around the central massive black hole binary, where there are like 10% of the stellar distribution, you have a very, the ratio of your the triaxiality is actually quite high. Okay, and this triaxiality, what it does, it makes stars diffusing in the lost cone much faster than on two-body scattering relaxation. And in fact, if you plot the hardening of the binary as a function of time, you see it's more or less flat. Okay, and also if you plot the result as a function of numbers, okay, because one of the problems of this embodied simulation is that the coarseness of the system, given the fact that you're simulating with 100,000 or 1,000,000 stars, a system that actually should have 10 billion stars, right, causes spurious diffusion. So one of the concerns is that the diffusion in the lost cone that you're seeing is actually driven by the numbers that you're using in your simulation. But it seems not to be the case, in a sense, in this kind of simulation where you're merging galaxies, because the actual hardening is essentially independent on the number of particles that you're assuming, whereas we would expect a trend with the number of particles to the -1/2 if your relaxation was driven by coarseness of the distribution. So,
small point.
sure.
It really isn't 10% of the mass of the galaxy inside the binary black hole. It's about 10 to the -3 or 10 to the -4.
No, this is a radius in which this is the triaxiality in a radius in which 10% of the galaxy mass is included in the model. So you have your galaxy. You take the yeah, that's larger. That's much larger than the binary. Yeah. Okay. So here the plot the point of this plot is to show the closer you move to the center after the binary after the merger, the higher is the triaxiality. Okay. So that was a result recently published by Bortolas. But in general, I mean, the thing that matters is that after these mergers, the system live in triaxial environments. So one piece of work that we did together with Fazil Khan is that, okay, now that it appears at least that to a large extent, these binaries after in a merger remnant, they evolve essentially in a way that would resemble the evolution in a sort of full lost cone regime. So can we actually make a link between the standard, full lost cone dynamics and the evolution that we see? This is what we did in this letter a couple of years ago. And essentially, the idea is that the vast majority of the stars that interact with the binary come from a distance that is of the order of few influence radii of the binary. Okay, and if the lost cone is full at that separation, then you should be able to employ the standard Quinlan formula 96 simply by rescaling your the density and the velocity dispersion with the density and the velocity dispersion of your system at the influence radius of the binary. Because we know from this seminal work of Quinlan to 96 that essentially the dA in dt driven by three-body scattering goes with equal a square times g rho, and then there is gh is a dimensionless factor, and then there is a density over a typical velocity of the background stars, which were like uniform in the Quinlan setup. And what we find is that if you replace these quantities with the rho density at the influence radius and the velocity dispersion at the influence radius, essentially what you find is a constant hardening rate with an hardening rate coefficient which is between 10 and 15, which is exactly what you get from three-body scattering experiments. So to a large extent, it seems that this post-galaxy merger behave like the binaries would evolve in the full Oscon regime. And I have to mention that there is a very nice piece of work, actually much nicer than ours, from Fabio and Eugeni Vasiliev and David Merritt, which actually goes more beyond, much beyond our treatment, and they find some decline of the rate at later times because you drop the density of the stellar distribution. But I would say that within a factor of 2, the picture is more or less consistent. Now, there are two key. So one would say, okay, so we understood the problem. There are two key problems here, though. So the hardening rate depends a lot on the density at the influence radius, and also the time scale depends a lot on this, well, F factor that I don't have time to explain, but is a strong function of the eccentricity of the binary. In the sense, if the binary is very eccentric, the merger time scale is actually much shorter. Okay, and I would argue that we don't know much about these two quantities for typical galaxies at the influence radius of the black holes. Especially, we don't have a clue what the eccentricity does. Okay, so I will skip a couple of things here, but if you put all these things together and you take typical density profiles for galaxies, and you try to compute what is the gravitational wave, the evolution timescale for subparsec binary as a function of the binary mass. Okay, here we go up to 10 to the 11. Don't forget about this. But you can go up to 10 to the 10. So you see that these are gigayears. Okay, and typical timescale of the evolution are of the order of gigayears, and there is this huge dependence on the eccentricity of the system. And one of the problems is that although on one side all the numerical simulations converge quite well when it comes to prediction of the evolution of the C-major axis, and the predictions agree quite well with theoretical understanding, eccentricity is all over the places. So the simulations very much depend on fine details. Even if you start with the very initial condition, you end up with different eccentricities. So it's much harder to solve the eccentricity of the system properly, especially the eccentricity at which the two black holes pair in first place. Okay. Well, I guess because you have a when the two black holes, well, there is certainly a coarseness problem, and eccentricity, really the angular momentum at the pairing of the system, where the energy of the orbit is about 0. Okay. So the eccentricity depends on a combination of energy and angular momentum. And since the binding energy is close to 0, the value of the eccentricity is very sensitive of, very fine, the corners. Yeah. So the bottom line that I want to stress in this first half of my talk is that we have a pretty, let's say, converged understanding of how the dynamics works, at least in first approximation. But is there an earthquake? But the eccentricity and but this depends a lot on the density of the galactic system. It's two black holes. They just merged. This was really, nearby. Oops, a North Korean binary. So no. It's gravitational wave. It's a gravitational wave. So, but the bottom line here is that these times can be particularly long, order of gigayears, especially for very massive galaxies that have very shallow density profiles. Okay, and this is particularly interesting for pulsar timing arrays, because pulsar timing arrays are actually sensitive to the binary, to the system that reside in this kind of galaxies. So yes. You see actually a stronger dependent on the binary mass. Or was it Merritt work? Can we take this offline? Because otherwise I will not have time to say what I want to say in my talk. Well, it really depends on the density profile, because that defines the sphere of influence, and then that's defined the density that you take there at the sphere of influence. So here we are using an Enquist profile. Well, is actually a Denon profile with different gamma for computing these curves. So, but
It's not a two-body problem.
we take that offline. Yeah. Sorry?
It's not a two-body problem in any case.
It's not a two-body problem. No, that's true. I don't think I got the comment. Anyway, now it's not a two-body problem anymore because if you have very long merger timescales, so the binary live a giga year, let's say, or giga years in this separation, then of course the hierarchical clustering will naturally bring other black holes in the problem. So this actually makes the possibility of triple interactions. Okay, so there has been actually already work about triple interaction in the past decade in the context of supermassive black hole binaries. I mean, the word of triple interaction in other contexts dates back in 50 years or so. So we decided to investigate more in the context of massive black hole binaries this issue together with a student in Milan, and there is a nice piece of work that Jerry was mentioning before by Ryu et al. That essentially does tackle the same problem from a completely different angle, and we find quite consistent results, which is nice. So what we did was to design a three-body integrator that was suited for this problem. So in particular, I mean, there are many three-body integrators out there, and the thing is that we wanted our own code to be able to include all the dynamics that we think is relevant for galactic nuclei. In particular, we had a simple prescription for dynamical friction. We have implemented a orbit average prescription to mimic the stellar hardening in the three-body phase. And then we include an external potential also for the, to include also precession of the binary that is done for now is spherical. And we include post-Newtonian dynamics up to the 2.5 pn order. And the nice thing about this is that we actually derive this 2.5 pn order self-consistently from the three-body post-Newtonian Hamiltonian. Okay, so we also have the cross terms. We are not just adding the 2.5 pn pairwise, as essentially is done in any other code. Okay, you can do that for the three-body Hamiltonian. Four-body is actually not as simple. Okay, so this is a code that our student wrote, and so this is an example of what he will show. I actually have a movie of that. Okay, so this is actually, I will use another code for demonstration. The code is currently courtesy of Cole Miller. Unfortunately, he was supposed to be here, but he's not here, so I cannot do the demonstration with his side. Okay, so this is a human three-body code that I just devised. So you see the system here, so you have a binary. Okay, circular binary, doesn't do much really, right? So now what we do, we take a third body in the system, right? And the third body approaches the binary. And as it approaches, you see the Kozai resonances are increasing the eccentricity, and that is exchanging with the more, and then at some point, Kozai, very eccentric merger, okay? And this is what you see in this plot here, okay? So this is a secular three-body interaction. Of course, you can have also more complicated situation. No. You can have more complicated situation where your binary comes, the third body comes, but at this point, is not efficient the Kozai resonances, so you have actually a complex three-body interaction of the system. And you can end up either with an ejection. I told me to be ready. Come on, Stefan. Or again, if you're lucky, with a merger, okay? Boom, end of the, so this is, it all works, I mean, no bugs, perfect three-body codes. So this is a typical example of the interaction. So we tested this code against many results in the literature. We tested all the stability of the triple configuration in PN approximation, et cetera, et cetera. We did some comparison with some specific run that Fabio did with Archain and other codes. And so it works pretty well. What we did was to do a full parameter exploration that is relevant for this kind of problem. So we ran several thousand of these three-body simulations varying the most relevant parameters, which are the masses of the three objects. So we have a mass of the primary black hole between 10 to the 5 and 10 to the 10, the logarithm, the inner binary mass ratio, the outer binary mass ratio, the relative eccentricity of the two binaries when when the interaction starts, and then the inclination of the relative orbit of the inner and the outer binary. Okay, so we did a very extensive study of the full parameter space, and so the results, I will give a glimpse, a little bit of the results summarized in a few plots. So this is as a function of the inner mass ratio and the outer mass ratio of the, so this is the mass ratio of the inner binary and the mass ratio of the outer binary. This is the fraction of triple interaction that ends up with a merger, okay? So you see it's up to 40-something% for equal mass binaries. And it's actually pretty constant as you go down in inner binary mass ratio, and then it drops a lot when the outer binary mass ratio becomes small, and that's simply because the perturbation of the third body is not extremely efficient in this case. So overall, the average over the parameter space, we find that more or less the three-body dynamics lead to the merger of one black hole binary in the triple in more or less 30% of the cases. Okay. One interesting thing that you can see here, you can actually disentangle the effect of the. So here, this is a secular interaction, like a Lidov-Kozai resonance leading to a merger, and this is a chaotic interaction. Okay. You can actually disentangle the importance of the two by considering the fraction of mergers in which you had an exchange between the black holes, which is indicative that there was a chaotic interaction, to the fraction of from the fraction of merger where there wasn't an exchange, that is indicative that there was a binary here and it merged because of Lidov-Kozai resonances. Actually, you see that these resonances are important in this plot here. This is the fraction of merger as a function of inclination, of the relative inclination of the two orbits. And you see this nice peak around 90 degrees, which is where you expect the resonances to be more effective. So if I now consider the fraction of mergers with exchanges and without exchanges for, let's say, system with low inclination and system with high inclination, what I see is that when you have an exchange, the fraction of mergers at low and high inclination is essentially unaffected. Okay. In the system where you don't have an exchange, you actually see this very bright blob here for equal external mass ratio, where you have many more mergers. And this is actually the fingerprint of the secular evolution driven by the Lidov-Kozai resonances. One thing that is actually quite important in this context is that as we said, our code includes all the post-Newtonian orders. And it's extremely important in this case to include the first PN precession term, because this really changes a lot the fraction of mergers that you get, especially at the low mass ratio. I'm saying this because there are works in the literature that didn't consider this, and they find actually a higher fraction of mergers. And you see the difference here when you don't include this post-Newtonian term, and when you do include the post-Newtonian term, you see that you largely suppress the evolution, the merger of the low mass ratio binaries. And this is because these binaries are actually are more compact. And when you include the 1PN term, the precession, the GR precession destroys the coherency of the Kozai-Lidov mechanism. So you actually suppress a lot of these mergers here.
Did you
Yes?
include gravitational radiation?
Yeah. This is a 2.5 PN. So there is also the quadrupolar term in the gravitational radiation. Yeah. And 1 minute. So what we can do then, we have this library of merging triplets. We can actually couple it with this very fancy scheme. Well, this is actually a model for the evolution of galaxy, a semi-analytic model for the evolution of galaxy and black holes. We can actually track with this semi-analytic model the evolution of the system, and we can actually see every time that you form a triple, you can actually implement the libraries that we got from the previous experiment and see what happens. So the first thing that we did was to investigate the terrible scenario for gravitational waves, which is what if these merger timescale are giga-years and actually binaries don't merge by themselves, right? So what you find is that you always form triples because in most of the cases you have a subsequent merger. And you remember in 30% of the case you make one of the binary coalesce, okay? And this was one of the results that we found is that if you employ this very pessimistic model to pulsar timing systems, what I plot here is actually a gravitational wave stochastic background characteristic strain as a function of frequency for two different models. So these are sensitivity curves of pulsar timing. This is the kind of signal that you would expect, for a typical merger scenario where black hole merge. And if you stall all the binaries, in which if you don't have these triple-driven mergers, you would just lose your gravitational wave signal. This was a big concern in the pulsar timing community. But still, you just suppress your total signal by only a factor of 2 because you have these triple-driven mergers. And this is very nice that this result in particular is very consistent with the result from Ryu et al. That consider the same problem for a completely different angle. One last thing that I'd like to mention is that another interesting thing is that you will have a lot of very eccentric binaries, some of which they might emit bursts in the LISA band. So this is the LISA sensitivity curve, and this is one of these eccentric bursts. And this is a kind of sources that wasn't particularly considered before. And the really last thing that I want to mention is that if you consider this three-body interaction in your merger trees, even if all binaries stall, and so here I refer to the model that Marta showed, the most pessimistic model that you saw in her talk where there were like 1 or 2 mergers, right? In that model, we didn't have the triple interaction. What you find is that even in this case where you have long time delays, with LISA, you always end up, and these are the bottom rates here, you always end up with order of tens, 100 events in a 4-year mission. So this can really work even as a safety net, if you want, for these gravitational wave experiments, in the case that that standard binary dynamical processes where you have binaries in stellar environments would fail. So I will just leave up my conclusion and take questions if there is any. Thank you.